Live streaming is on.
All right, and welcome everybody to the second last tutorial for Transform 2022. Today we're going to look at Julia for geoscience. Before we get onto that, Transform 2022 is a digital conference type thing with around digital geoscience, so online conference around digital geoscience with everything being as openly accessible as we can make it. So tutorials are being given on YouTube or as live streams, which if you're catching now, hello. If you're watching this in the future, awesome. Um, so many thanks to curvenote.com for helping us out with this. For their support of Transform. You can find the schedule and everything, so you can see what tutorials you've missed if you haven't caught them live at softwareunderground.org/transform. If you're wanting to get involved with the community in general, you can join our Slack, softwareunderground.org/Slack will get you there, and then look for #T22 channels. Remember, you can pause and rewind these videos if you miss something. That is, even if you're watching this live, you can still rewind a little bit. But I'm going to hand over to Francis Yin, who will take us through some Julia for geoscience. I'm quite excited for this one.
Great. Thanks, Martin, for introduction. My name is Ziyi, and people usually call me Francis because it's easier to pronounce. I'm a third-year PhD student at Georgia Institute of Technology, advised by Professor Felix Herman. And my research interest is, in general, inverse problems, scientific computing, deep learning, and their applications in time-lapse seismic monitoring of carbon storage and sequestration. And today I'll talk about Julia for geoscience, which is something that my research is based on every day. And actually, when I joined the PhD program at Georgia Tech, I came from a math background. I didn't know anything about geoscience, anything about geophysics. Like when the group members talked about these seismic migrations, full waveform inversions, I had zero idea of what they're talking about. But I'm very glad and appreciative that the group members in our research lab built these fancy Julia software stacks that built every seismic tutorials and also seismic inversion softwares in a very abstracted way, so that I don't have to be overwhelmed about solving these seismic migration problems, solving these seismic imaging problems. Literally, with these correct Julia software abstractions, I'm just solving AX equals to B. So that's the idea I want to convey in today's tutorial. How can we use Julia to abstract the physics or geoscience applications, and how can we incorporate that with some deep learning frameworks, things like that. Okay, let me share my screen now. I hope people see my screen right now. And today's tutorial is placed in this GitHub repository called Slim Tutorials. We actually had a bunch of them from 00 to 11. This is like a software stack that our group uses. And today, I'll mainly talk about 5 of them, namely Intro to Julia. As I promised, this will be a beginner-friendly tutorial about Julia for geoscience. And then I'll talk about Intro to Jolly, which is a software for linear algebra abstractions. And then I'll talk about Intro to Judy, which is a software abstraction framework to run DeVito in Julia. So Judy is actually a software for these large-scale seismic conversions and seismic imaging. It calls DeVito underlying. So if you actually heard about DeVito workshop, DeVito tutorial in the previous, I think, Tuesday, then it would be good for you to pick up your memory from there and then go to the Judy, which is really running DeVito in Julia in a quite simple and clean way. And then, since this tutorial is for geophysical community, I'll talk about how we handle these sec.y files in Julia. So sec.y file is one of the file format that geophysicists use a lot to store seismic data, for example. And we have a quite clean way to handle that in Julia, and that can actually talk to Judy, which is the seismic inversion framework. And in the end, I'll talk about basic normalizing flow training and sampling, which is something about deep learning. So normalizing flow is a type of invertible network. If you've never heard about that before, it's totally fine. I'll introduce these details in these scripts, so don't worry too much about them. And basically, we're going to run these tutorials in IPY-ND files, so we'll do these in Jupyter notebooks. And there's actually a Julia kernel in Jupyter notebooks. Well, actually, the JU letters in Jupyter is actually for Julia. So we'll do this in Jupyter notebook, but if you're in a crunch of time, you don't have time to install the packages or install Jupyter notebook, we provide these Docker images that have a lot of these built-in packages already in there. So you can do this Docker run. This will basically bring you with a link that you can copy paste to your browser to run Jupyter notebooks. And if you are more interested in running things into the terminal, you can also use the Docker image to run the terminal. That's also fine. So basically, this is the Docker image to go. And if you want to install some packages, well, I'll talk about it later. Okay. So let's start by introducing Julia. So Julia is actually a quite new language. It was born in 2009 by some MIT researchers. In a nutshell, Julia is designed to be fast, to be dynamic, reproducible, composable, general, and open source. So I think from my user experience, Julia wants to be a language that is as fast as C or Python, and as fast as C or Fortran, and as easy to use as Python. Julia wants to do something that get involved into these both worlds. And its download installation is actually quite simple. It's open source. It's not like MATLAB, which requires this license. You can just do download right here. And there are actually a lot of versions of Julia right now. And Julia keeps updating itself quite frequently. So the current release is version 1.7.2, which was released in February 6th, 2022. So quite recently. And you can actually follow the instructions here to install it on the system. For example, I'm using a Mac, so I'll just do this one. I click it, and then it'll install something for me. Then I just do opening. And then in the end, I just install Julia in Mac as if like I install an application into my Mac framework. And you can also follow other tutorials, these installers to install Julia on your system. And Julia has this long-term support release, which is version 1.6.6 released last year. This long-term support means if you find some problem about, for example, this matrix vector product really doesn't work as you expected, then after this version 1.6.6, you can reach out to Julia community and they'll definitely support you to solve your problem. And there's this upcoming release, which is 1.8. It was released in March 29th, but it's in beta version right now. So we can pretty much expect it to be released in next few months, for example. Okay, after you install Julia, you can actually run Julia in several versions. So you can run Julia in a terminal like this. I open the terminal and make it big. You can do Julia, and it will basically call out this Julia REPL, which is an interactive framework where you can run commands line by line. And you can see my version right now is 1.7.2. Then you can run some command like print, hello, this is Julia. Great. And then you can do exit to exit this Julia interactive REPL. And then you can also write a script. For example, you can do touch script, and you can do the same thing. Print hello welcome to Julia. Okay, then the script will be a sentence in Julia, right? Then you can do Julia script. Perfect. The script is run and it prints out, hello, welcome to Julia. And you can also do this. You can do Julia and you include one of these script you just written. So include script.jl and it'll do the same thing. So this could be a very long Julia script. You can do include. And what else? You can also run Julia in short sentences by this Julia-E. So basically this -E will evaluate things in this single quotation marks. So you can do println, hello, Julia. Same thing. Okay, great. And then you can also run Julia in Jupyter Notebooks based on its Julia kernel. So the way you do Julia, these Jupyter Notebooks, is you have to install one of the packages in Julia called iJulia. So right here, let's talk about Julia's package management a little bit, since I assume a lot of these audience will be new to Julia. That's no problem. So in Julia, there's you can have different ways to call out the package management system. So if you press the right square bracket right here, this one, now I actually press the tab, press a space. But if I don't do the space, I just do the right hand side of the square bracket, it will call out this package management system. And then you can do the command add iJulia to install this iJulia package, which gives you that Julia kernel in your Jupyter Notebook. And this add command is actually a way you add a Julia package into your system, right? Then you can actually live in this framework. You can do rm, which is to remove a Julia package. I can remove iJulia. No, I won't do it this time because I really need that. But you can do remove to remove a package. And what else? You can also run shell commands in this Julia interactive framework. You can do the single quotation sign on your keyboard. Sorry, semicolon, my bad. You do this semicolon on your keyboard, and then it prompts you to a shell script. And then you can do PWE, for example, show up my rule and ls, a lot of things. Okay. And then what else? There's this, if you do a question mark in Julia, shift question mark, it will basically prompt you a help. So you can search for functions that you're not sure in this way. For example, if I'm not sure about how this function println works, then I'll just do help println, enter. And then it will say, well, println is trying to print something right here, which is XS. So you can, for example, you can do print hello world. So if you do shift and this question mark, it will prompt you to this help. So you can search for functionalities over here. Okay, I think this will be the Julia interactive part. And then let's go to Jupyter Notebooks to check our tutorials. So you can do Jupyter Notebook. Then it will prompt you to here. My desktop is kind of messy, but my tutorials is right here, Slim Tutorials. And I'll first talk about Intro to Julia. All right. In this notebook, I'll basically talk about 5 things. So first, I actually alluded a little bit just now, how to use, add, remove, or develop a package in Julia, the package management system. And second, I'll talk about how basic linear algebra runs in Julia, since this is beginner friendly. Then I'll introduce you to the just-in-time compiler that Julia uses that is quite different from some other packages, other software languages, for example. And then at last, I'll talk about multiple dispatch, and type stability that makes Julia run very fast in a smart way. Okay, let's begin by package management. So we already see here, when we want to use a package in Julia, this is like import in Python. We just do using, and then we can call several packages: linear algebra, test, benchmark tools. We'll do benchmark tools a little bit later. Okay, this is using, which is the same as import in Python. And then we can run this line. Hope it runs okay. Okay, it's okay. And then to add or remove a package, we already discussed this a little bit just now in the Julia Interactive terminal, but we can also do this in scripts. We can do using PKG, which is the package management system. It's a package, and you can do PKG add a package. So this is the same as if you do this. This is the same. You just do add iterative solvers, then it actually does the same thing as if you do it here. Okay, if you do this pkg.add, it will add this iterative solvers package into our system. And similarly, you can do this rm, which is remove, to remove a package from your system. As we showed just now, you can also do this in the Julia Interactive ones. And what else? You can also install a package called iterative solvers, same package, by a specific version. So you can specify a version 0.9.2 to Julia. Say, Julia, you have to install this version. And then Julia will install this specific version. And finally, you can add a software package by its, just shows the output. You can add a Julia package by its GitHub repository link. So this is actually a link for iterative solvers, and you can specify that and add, also specify a branch of that. Then the Julia can install whatever in that branch of this repository. So these are the several ways to install packages into Julia. And similarly, you can do this by the square bracket add, or square bracket remove, square bracket add a GitHub repository. Same thing. Okay, this is what Julia package management system looks like. The next part, we'll be talking about linear algebra in Julia. So the way you set up a Julia vector or matrix is actually quite similar to the way you set them up in MATLAB. So if you ever seen MATLAB, you also use the square brackets to denote matrix or vectors, and you use this semicolon to change rows, basically. So I can write a matrix A in this case, which is 1, 2, 3, 4. And this semicolon changes the row. So basically the first row will be 1, 2, and second row will be 3, 4. This is how you set up a matrix in Julia. And Julia actually stores these multi-dimensional arrays, including matrix, in a column measure order. Meaning, when we read this matrix, we read 1, 2, 3, 4, but actually Julia stores this matrix by every column into its memory. So the way it stores is 1, 3, 2, 4. So if you do this A, if you vectorize A, this matrix A, by the square brackets and semicolon, it actually shows you this 1, 3, 2, 4 structure that Julia actually uses to store this matrix A. So this is a functionality to vectorize a matrix. And you can also do the same thing here. This is another function that vectorizes A that does the same thing as this cell. Okay, let's run this. All right. And then you can also write a vector here, which is called x equals to 1 and 2. And Julia always assume the vector you write into Julia is column vectors. So if you take the shape, it will be 2 by, it will be 2, but it assumes this vector is a column vector. Then there are also these built-in basic linear algebra operations like MATLAB or Python. You can calculate the inverse of a matrix, and it will do things like this. You can do matrix vector multiplication. So in this case, A is here, 2 by 2. And then X is here, which is a column vector of length of 2. Then you can do A times X, which gives you this 2-element vector. And then you can also do A backslash X. This actually follows similar syntax in MATLAB. The backslash is to solve the system A times something equals to X. And it solves this system by least squares. So you do A backslash X, it will give you basically A inverse times X. Okay. And you can also have these determinant of the matrix A. So we have all functionalities of matrix A, of linear algebra in Julia. Then that's the second part about linear algebra. Then the third part is actually one of the quite interesting thing in Julia. So Julia used this just-in-time compilation techniques that is quite different from C or Python. If you think about you run a C script, then you have to compile the C script from the first line to the last line first before you run the script. After you run the compilation of the entire script, you would run the entire script. So for C, you have to compile, then run. But Julia used this just-in-time compilation. So let's see how it works. Suppose I want to do this matrix vector multiplication, where A is a random matrix that uses float 32 as its type, and it has these many rows, these many columns. And B is a column vector, which is in type float 32 and these many entries. Then we can actually run A times B, like we talked about before, right? And then we can use the macro time. So at time will basically tell you how much memory and how much time you use for this operation. And let's do this up. Okay, you can see this operation takes 0.11 seconds. This is actually the first time we run this line, A times B. Then if we do a second run, you can see a much shorter time for you to run this line. And you can actually do this multiple times. You can always see, well, it's just about 0.02 seconds. It's not something like 0.11. So what happened is when Julia tries to run this matrix vector multiplication, Julia never runs this function before, this multiplication before. So if you want to run it in the first time, Julia have to compile the function of multiplication first. And then after the compilation, it runs this function. So you can actually see here, it takes these many time to compile the function that aims to multiply the matrix and vector. But in the second run, since this function is already pre-compiled from the cell here, you don't have to compile it anymore. And then you can just do run itself. So it takes you a much shorter time and much less memory allocation in your operation. And this is a bit weird because we actually run something like matrix vector multiplication before in this script. We just talk about the basic linear algebra. We set a 2 by 2 matrix, we set a length of 2 vector, and we did this matrix vector multiplication before. I thought it's some function that is already run before, but why does Julia still think that it needs to compile this function in this cell? It's a bit weird, right? So let me explain it this way. We'll discuss this in the next session about multiple dispatch. So basically, Julia considered the matrix vector product here different as this matrix vector product, because the matrix A here, which is defined as this 1, 2, 3, 4 matrix, 1, 2, 3, 4 matrix, it's in type of integer. And similarly, you can check in this cell, we define a vector called 1, 2, which is also integers. Then when you do this matrix and vector product, it does the multiplication of a integer matrix and an integer vector. So that's actually a very specialized multiplication. And Julia will definitely think that, okay, I've already done integer multiplications at this moment, but I haven't done any float 32 multiplications at that moment. So Julia still thinks this is a brand new method for it to run, so it needs to compile. So we can do another experiment here. We can initialize A as a random float 64 matrix. Again, this is a new type that Julia never seen before. And we can also initialize B as a float 64 vector. Then, after I run this cell, I can do time, A times B. So again, let's run that cell. You can again see this very long compilation time in the first one. Why? Because Julia have done these matrix vector multiplications for float 32 before, for integers before, but it just never see anything about float 64. Then in the end, Julia still thinks this multiplication is very specific. I have never seen something before, so I have to compile it first. So this is a way how Julia runs. So if you run the same cell again, you can see very shorter time this time because Julia already done something before, done this multiplication before. So Julia has no problem of running very fast in the later runs. So the takeaway message from this small experiment is Julia used this just-in-time compiler. So when Julia sees a sentence, Julia will think about, well, have I run this sentence before or this method before? I have to run this method and it's exactly the same way it's typed. But if I see a new type, I still think I haven't run this function before. Then I will need to compile it first and then run. So that's the way how Julia just-in-time compilation works. It's not a stupid thing, but I'll show later why it's actually a smart thing. So the next thing I'll talk about is this benchmark tools. So basically, we just discussed at time, this macro is a way to take the memory allocation and time from an operation, but it only takes one time, like the current one. So if we want to benchmark a function, the runtime of a function, then we better use this at benchmark macro from this benchmark tools package, which actually gives you a very beautiful histogram that takes 200 samples about these multiplication with one evaluation. And then in the end, you can get the median of the runtime, mean of the runtime, things like that. Okay, this is how Julia just-in-time compilation works. Then I'll talk about multiple dispatch, which is one of the core things in Julia that makes Julia kind of different from other languages. Okay, so what does multiple dispatch mean? As we just saw, Julia uses different multiplication method for different typed input, right? If you give it to float 32 vectors, it's different from you gave it to integer vectors. Julia will still do the multiplication, but use different methods of multiplication. And we can actually do a small experiment here. We can do a scalar multiplication, 1 times 2. And then we can use this at which is a macro, to ask Julia, which function did you run? Okay, let's run this. So in this script, basically the Julia tells you if you want to calculate 1 times 2, it uses this function, which is x times y, and they follow the same data type, where the data type is a union of all the integers, int. This means basically Julia uses the integer multiplication for this 1 times to 2. But what about this cell? We still do the 1 times to 2, but we put them in float 64. Then which of Julia basically tells you, now I use a different method to compute this multiplication. I use this multiplication of 2 float 64 instances, which is different from the previous one. And then you can actually run this 1.0 times to 2. You ask Julia, which function did you use to run this multiplication? Julia will basically tell you, now I use a generic function to run this. Namely, I assume x and y are both generic numbers. I have no assumption on what their type is. And this is actually one of the instances, one of the situations that we want to avoid if we insist to run things in Julia. Because Julia is very good at generating compile these functions where the specific types are provided into the functions. So if, for example, this one, Julia knows that these are float 64s. So Julia has this specific way to compile the function just for float 64. But if you actually provide 2 generic instances, then Julia doesn't have a specialized way to compute this multiplication. Then Julia will basically choose the most generic way, which is not good, because you want things to be specialized in Julia. So Julia can find the very specialized way to compute your multiplication very fast. So this is actually kind of instance we want to avoid in Julia. And then we actually have another example, which is a full example. We can define a full function which works for different kinds of input. So let's again think about multiple dispatch in this case. So I define a full function which takes 2 strings and print out my inputs are strings. Then we can see we define a full function which is a generic function with 1 method. And then we can do full. It takes 2 strings and it gives you the correct output. But now, if I want to run this full function for 2 integers, the Julia will basically complain, no, I haven't noticed any method to run this full function for 2 integers. That's because we only provide a function to run these strings. However, you can actually add another method to full, which works for the 2 integers. Basically, you define this line. Now, the full 3-4 will work because we have this function right now. And you can actually see the output from Julia. Julia says, well, this is a function full. It's a generic function with 2 methods. Where are these 2 methods? These 2 methods are the full for strings and full for integers. Okay. Now, you can still run the previous script. You run full hello hi, which is the thing we run just before. And you can see this method doesn't get overloaded. It's still there. It's a different method, so it won't be overloaded, although it's under the same generic function. Okay, there are also another example that I put here. I will skip it because I think we already understand how Julia multiple dispatch work, but you can feel free to test it out to understand it a little bit more, how to write Julia functions in a smart way. Okay, next thing I'll talk about is type stability. So by type stability, I mean we should always write type stable code such that Julia can easily infer all the variable types in your function. Then Julia can generate very specific kind of code to compile, then run very fast. Okay, suppose we want to define a function called function n, which takes a sequence of numbers in this case, and this ... is a splatting operation, which separates out your sequence of numbers. And then we want to compute the product of the entire A, then we can define a function like this. We define an intermediate variable C, which copies A1, the first one. And then for every instance of this array, we can do C equals to C times AL, where AL is the instance. Then we can compute the product of the entire sequence, right? Okay, let's run this. Then we can do a benchmark on this sequence, 1, 1.5, 2, 2.5, 3. Okay, it takes this nanoseconds, which is very short, great. Then we can run this script, which is a different X, but the same input, basically, the same numbers. Now I run the benchmark here. It takes a much shorter time than this line. It takes only 200, then 300. So what happens? Basically, we can see that all the inputs in this array are float 64, where the instances in this array, 1, 2, 3, they are integers. So this is one of the situations that Julia doesn't really like to run this kind of code. You can actually use the macro called code warn type to see what's the problem. So if you run function nx1, basically run this x1, which consists of integers and float 64, you can actually see a lot of red things in the output, which means Julia warns that there's type conversion in several lines, which Julia hates to do. But if you do the same thing for x2, you can actually see there's no warning in here, meaning the code is type stable. So let's go back and try to interpret what happens. In this case, you first initialize your C as the first instance of your sequence, right? So if you actually run this x1, the C will actually be initialized by 1, which is an integer. And then after you run the C equals to C times AL, C finally becomes a float 64 because there are a lot of floating point numbers behind. Then Julia actually did this type conversion, which it hates to do. So Julia isn't sure what type of C it outputs. Then Julia doesn't have a specialized way to compile this code. It just used a very generic way to compile the code. In the end, it won't be fast. But if you actually initialize C as a float 64, like here, it's 1.0 at the start, then the C will always be a float 64. So in the end, things will run without any warning types. So that's what type stability means. So when we write code, we want to write this type stable code that Julia, it's easy for Julia to infer every variable in your function. Then Julia will find a very good way, efficient way to compile your code, your function. Okay, that's something for intro to Julia. I'll directly go to the next one, which is intro to Jolly. And have a coffee. Okay. After we talk about intro to Julia, I think people understand Julia a little bit. It has this multiple dispatch functionality that takes different, when you define a function, you can take different kinds of input, and that's a different method under the same function. And also, you want to make sure that things are type stable, so that Julia has this specialized way to compile the code. And this script is basically an introduction to this jolly.jl package. You can find it here under Slim group. Actually, you can find a lot of packages used today in the Slim group GitHub. And it's a way to construct matrix-free linear operators with explicit domain and range type control, and apply them into basic linear algebra matrix vector multiplications. So with this explicit domain and range type, Julia actually likes it pretty much, because it's always good for Julia to know what kind of things you're running under the hood, what types of variables you're using, right? Okay, then in this script, we'll talk about 3 things. First, how to build a linear operator in Jolly and verify its correctness. And then second thing, how to solve a linear inverse problem AX equals to B, where A is not a matrix, but a linear operator defined by Jolly. And third thing is how Jolly interacts with machine learning toolbox like Flux in Julia, which is the combination of PyTorch and TensorFlow in Julia, because Julia only has one of them, and optimization toolbox, which is called optim.jl via chain rules. A lot of details right here. So basically, Jolly is a linear algebra package, which inherits the same idea of spot if you familiar with MATLAB. So spot is actually another matrix-free. Well, I don't think this is it, but maybe this one. Yeah, spot is basically another linear algebra matrix-free package designed from MATLAB, and surely inherits the similar idea of that. Okay, let's begin by loading a few packages and try to build a linear operator. So this could be one of the examples that geophysicists are interested in about deconvolution. So we can actually do a convolution example in this script and try to invert for it, which is deep convolution. Okay, let's first build a convolution kernel and a convolution operator by the Jolly toolbox, which is this linear algebra framework. Okay, let's first set up a convolutional kernel. This is the time interval, the length of the time, and also the time vector. And this is the convolutional kernel, and you can plot it actually. So basically, Julia uses the pyplot package for plotting signals or images, and it actually calls out this foreign library in Python called matplotlib. So the functionality is already the same because it uses this foreign pycall. Okay, then you can see there's a convolutional kernel we just built for 2 seconds. And then we want to build a linear algebra, this matrix-free linear operator that does a convolution on a random matrix. So that after I build this matrix, I can multiply it with a vector x. That's our end goal. But we don't want to construct an explicit matrix because this convolution could be dense. And right now, this is a very small scale example. But imagine if you have a convolutional kernel of billion entries, then your dense matrix will be billion by billion, which is something you just don't want to store in the system, right? So all of the ideas of concepts of Jolly is to design a linear operator, which is not an explicit full matrix, but this matrix-free linear operators that are that provides the adjoint and forward evaluations of the linear algebra of this matrix linear operator. So let's talk about convolution a little bit. I think if people are familiar with Fourier transform, the convolution of two signals, it can be easily computed in Fourier domain. You can actually take the Fourier transform of these two signals, do an element-wise multiplication, and then you can do an inverse of the Fourier transform. This basically gives you the convolution of W and X, where W is the convolutional kernel right here, right? Then we can actually write these in a very abstracted way by Jolly. So we can so our end goal again is to design a linear operator that does the convolution with the kernel of W. Now we can write it in a very abstracted way shown here. We can wait. Did I run this? Okay, I actually run this. My bad. We can actually define a Fourier transform matrix by Jo DFT in Jolly. So this is a linear operator provided in Jolly that makes a linear operator called F. And this linear operator F isn't a full matrix, but a linear operator equipped with forward and adjoint evaluations. So it's matrix free. And the second thing you can define with Jolly is Jo diag. Basically, it defines a diagonal matrix with its diagonal as this. So in this case, we want to do an element-wise multiplication. So we will define a diagonal matrix with FFT of W. FFT is the Fourier transform. So this Jo diag basically acts this element-wise multiplication on the Fourier transform of X. So in the end, if we want to define convolution, we can define this convolution by 3 objects, 3 linear operators. So first is a Fourier transform, we take this x to its frequency domain. Then we do an element-wise multiplication with the Fourier transform W, which is defined as a diagonal matrix right here, W. And in the end, we do an inverse Fourier transform so that we get the convolution of W and X in the end. And this is quite clean because you actually see this as the way you would interpret them in the linear algebra operations, right? This is a matrix A, matrix adjoint, matrix. Although they're actually not matrices. Jolly actually views this as linear operators and they're matrix free. Okay, so in this way, we can actually store these linear operators in much less memory because we don't have to store the explicit entries in the matrix if the matrix is full, right? And we can actually use these linear operators, as I'll show below, to do these iterative solvers and things like that. Okay, then in case you want to build a linear operator which doesn't appear in Jolly, although I would strongly suggest you to check the Jolly reference guide. There are a lot of linear operators that are built in Jolly already, such as restriction operators, comparative sensing matrices, Fourier, wavelet, curvature transform. They're already built as linear operators in Jolly. So in case you don't find something that doesn't live in the Jolly reference guide, you can actually build something on your own. You can build a linear operator in Jolly on your own. So suppose in this case, we want to build a linear operator that is a full dense matrix. Although it's a simplistic example, it's actually a dummy example. It doesn't make too much sense, but this is just telling you a way to build a Jolly linear operator. So suppose this is the matrix, and we can actually build a Jolly operator, linear operator M1 by this Joe linear function forward A. You will basically provide the size of the input and output, which is both n, makes sense? And then you will provide the forward evaluation of your linear operator and the adjoint evaluation of the linear operator. So these are both functions. This says you input x, I output you m times x. This says you input x, I output you the adjoint of m times x, forward and adjoint evaluations. And you provide, again, the domain and range types and the name of your operator. Then in this way, the M1 will be built as a Jolly linear operator. And then you can actually take the size of M1, domain type, range type. These are all Julia native functions and all overloaded in Jolly. And then you can actually do the linear and adjoint test on this operator M1. So you can check here, we select two random vectors, and then we do a linear test, meaning I use this linear operator to multiply each of them. Does that provide me the same output as I multiply it with the summation of them? And adjoint test, we actually use dot test. Basically, we test whether you take the dot of A1 and forward evaluation of this M1 on A2 provides you the same output as you evaluate the adjoint first on A1 and then do a dot with A2. So these are the linear test and adjoint test to make sure that your defined function, your defined linear operator is actually a linear operator, right? And after these tests pass, you can actually Jolly also provides these testing functions so that it generates these itself and just give you the test result. So if it doesn't throw you any warning, that means the test already passed. Okay, so what's the point of building these linear operators? Let's think about it again. So right here, we build a linear operator in Jolly with specific input and output size, domain and range type, and forward and adjoint evaluations, right? Why do we want to use Jolly is these forward and adjoint evaluations might not be this full matrix vector multiplications. It could be these abstracted functions. For example, if we want to define a Joe DFT, then the forward evaluation will be FFT on X, which can come from a foreign functional call from this FFT library of Julia. And this adjoint evaluation can also be IFFT because the adjoint of 4A is inverse. So these functional calls can be actually stored very cheap in your memory. This doesn't need to store all the entries in your matrices. Then in the end, your Jolly linear operator can be cheaply stored in your memory, while you can still have access to the forward and adjoint of your Jolly operator. And actually, if the Jolly operator is equipped with forward and adjoint, this is already enough for you to solve most of the inverse problems with these complicated, fancy gradient-based optimization algorithms. So next, I will show how to solve an inverse problem with a built Jolly operator. So remember, we already built a Jolly operator A with the Jolly toolbox that corresponds to the convolution with the kernel W, right? And now we can actually do a deconvolution, namely we observe some convolution result called B, and we want to infer which signal X does this W convolve with to get this B. So this is deconvolution. It solves an inverse problem as AX equals to B. And we'll show that you can just use Julia native iterative methods to solve these without any complications, without any overload, because things will work out of the box. So let's first play around with this small scale example. You have a ground truth X. Now in this script, I actually made a very sparse X so that we can test out different algorithms. Again, this notebook is not a competition of different algorithms. It's just a notebook to show that we have access to these algorithms and we can apply them with ease. So in this case, I set up a ground truth X, which is sparse, which is this long, and then I pick 20 non-zero entries in this vector. Okay, then I put these random 20 entries, non-zero entries at random locations in the signal with random amplitude. Makes sense, right? And then I plot the ground truth X, which is shown here. So this will be the X in your inverse problem, which you'll never know in your real life, right? And then you can actually convolve this X with the kernel W by applying A to your X. Then you get a convolved B in the end, right? And then actually, if you look at this slide, this is actually very plain linear algebraic abstraction code. So you can generate a noise term in this case, which is in the amplitude of this times a random vector. And then you can actually generate an observation vector B by A times X plus E. So everything is pretty much linear algebra. Julia doesn't even notice that our A is not a full matrix. Julia doesn't even notice this is a Jolly linear operator, right? Because the Jolly linear operator is already provided by the forward and adjoint evaluations. Although Julia doesn't know what the entries are in this matrix, it knows how to compute A times X because it's equipped with forward evaluations. Okay, now we get this noisy measurement. We can actually try out different algorithms in native Julia packages. For example, LSQR. LSQR is a very good algorithm to solve for least squares, inverse problems, to find a minimal two-norm solution, right? So this LSQR actually lives in this iterative solvers package. And then you can just apply LSQR A, which is the linear operator. Again, A here is a Jolly linear operator. It's not a full matrix. And B is the observation you just generated right here. And then you can actually run 500 iterations. Then, sorry, did I define it above? Did I run this? Oh, I didn't run this. Okay. I don't want things to crash. Okay, that makes sense to me. Now you can actually run this LSQR with your predefined Jolly linear operator and observation B. Notice that this A is not even a full matrix. So we actually kind of fooled Julia by providing a linear operator to Julia instead of providing a full matrix. Julia doesn't even notice that, but it still runs the LSQR in each iteration. Basically, Julia evaluates the forward of A, we provided already, and also the adjoint of A to take the gradient. We also provided that. So in the end, you can just use the native Julia LSQR method to invert this linear system and generate a solution. Then we can actually plot the solution from here. You can see that, well, although there are some spikes in your solution, there are a lot of these oscillations, which is white noise, because which tends to be like a white noise because your ground truth signal is sparse, and your LSQR algorithm aims to find a minimal two-norm solution. So this is what LSQR can get in the end. And then we can actually try out different algorithms. We can try out a algorithm called SPGL1 from this package. You can actually see, we also provide the linear operator A, which could be a matrix, or a linear operator as we designed above. And the observation vector B, which is also something we already got, and some options. How many iterations? Do you want things to be verbose? And then you can run this SPGL1 algorithm very easily, because we already equip this linear operator A with the forward evaluation and adjoint evaluation. Then in each iteration, Julia already knows how to compute it, although the A is not a full matrix. So in the end, we can get a solution from SPGL1, which is sparse. Makes sense, right? Because SPGL1 is an algorithm to promote sparsity in your solution instead of promote a minimal two-norm like LSQR. Then in the end, you can find a very sparse signal in your solution, which is great, right? So we already see that after we build a linear operator in Jolly, we can actually use this iterative methods to solve for the inverse problem where this Jolly operator is a forward operator, is the A in your inverse problem, right? And then we can actually play around that a little bit with automatic differentiation and also machine learning toolbox. So in this case, we want to play around with a little bit with the package called chain rules. So when we work with, for example, machine learning, we build a network, we give an input to the network, and this input is passed through these all different layers in your network. You get an output, you compute an objective function, and then Julia uses back propagation or any other, for example, PyTorch or TensorFlow. They use this back propagation to propagate the residual, the objective function back to every layer. Then in the end, when it's back propagated to the input, it's the gradient. It will be outputting a gradient of your input. Then you can update your current one with the gradient by any gradient-based optimization algorithm, right? Similar thing can happen here. So we can actually try to make something fancy or complicated as you wish. So we can minimize this two norm of AX minus B, which is definitely something we saw before, and then add a penalty term called lambda times one norm of X. This might also promote some sparsity in your solution, right? Because we add a one norm penalty on your solution. Now things might be a little bit complicated because if you want to solve this with an iterative algorithm, you have different choices. And if you want to take a gradient with respect to X, you can't because this one norm isn't differentiable. But you can actually use some Julia native packages like Optimum which provides you a lot of these optimization algorithms, gradient-based optimization algorithms. And as long as you provide with it a function value and a gradient, like it tells you, you tell them how to calculate your gradient, then actually you can use LBFGS algorithm to solve for these inverse problems. So let's show a small example. We put lambda equals to 1. Let's run the cell first. We put lambda equals to 1 here, and then we can write the loss function. We tell Julia what is the objective function you're trying to minimize, which is a half of the 2 norm of the residual square plus lambda penalization parameter times 1 norm of x. Makes sense, right? And then you can also tell Julia how to take your gradient, right? So this is an in-place gradient function that LBFGS algorithm needs in every iterations. So G will be the gradient, and if you add this sign, it will be in place. So provided with the current x, we can actually use this gradient loss, which is the loss function you defined above, x, which is your current x, and then you provide 1. So this basically takes the gradient with respect to your x and provided the loss function here. So we can do G gradient equals to this, and we return the loss. So basically this function is an in-place gradient function which outputs the objective function and overrides this G with your gradient. So after you define these two functions, one is for objective function, the other one is for gradient, you can actually use this optimize from this Julia native optimum package, provide the function f and how to calculate the gradient, the delta loss, the initial guess, which is zeros, and provide an algorithm, which is LBFGS, and you add some options, run, for example, 500 iterations. Then you can actually run this line. This line works perfectly because you've already provided the gradients and the function value. Then LBFGS basically knows how to optimize for x, provided the function value and the gradient. And you can actually plot the solution here, which also looks okay. But there's something magic happening here. Namely, I think you might already have some question about this line. Like, how does Flux know how to compute the gradient of the loss with respect to x? This loss is such a complicated function. Well, I understand automatic differentiation can differentiate through 1 norm or 2 norm. But when it sees something like A, which is not a matrix, it's a Joly operator, how does it know to compute the gradient with respect to this x? It's complicated. No one taught Julia before how to differentiate with that, right? But we actually add this overloading in Joly by chain rules. So if you actually check this script in Joly, this is quite simple. So this R rule is basically a functionality in chain rules package, chainrules.jl. So the idea is when you compute A times V, which is the forward evaluation of your Joly linear operator, you just have to tell it when you backpropagate from next layer, this Y layer, you just have to apply the adjoint of your linear operator A on your residual. And that's it. Because when you take a gradient with respect to this linear A, then you just have to apply the adjoint. That's one of the simplest rules when you want to compute a gradient, right? So given this R rule, we already taught Julia how to differentiate through a Joly linear operator. Then since Julia knows how to differentiate through A, Julia can differentiate through everything into this loss function. It knows how to differentiate through norm, how to differentiate through minus, and since we taught it how to differentiate through A, it knows everything. how to differentiate this loss function. So right here, this comes very smoothly. And then you can use this BFGS to solve for this inverse problems. So I'm not claiming this is the best algorithm to solve this kind of problem, but we just want to show that we can do this very smoothly. And then the next thing we can discuss is the AD capability, meaning we can actually incorporate these Jolly linear operators without their complicated networks and such. So if you actually read into some machine learning literature, there's a method called deep image prior that was raised in 2018 by these authors. And in our research group, we also incorporated this deep prior thing for seismic imaging. So we use this deep prior as a regularization parameter for seismic imaging. You can check this publication for details. But the basic idea is instead of solving AX equals to B, we solve A times F theta Z equals to B with a fixed Z, a random input. And we minimize this residual with respect to theta. And after a lot of iterations, we get a very good theta that fits this residual, then F theta Z will be our solution. So actually we can implement this with Flux, which is the machine learning toolbox in Julia. So we can define a very simplistic network right here, which is a dense network, take input 2n and output n. And then we can initialize Z as a fixed input, like here. Okay. Then we set up F, the network, in train mode, and theta will be flux.params. Basically, theta is the network parameters of this F. So F here is a dense network, then theta will be the weights and bias, basically. This is a simplistic network. If you want to really get the full functionality, you should put F as a UNet or something, but this is just to show how you can run things. So you can actually choose one of the optimizer from Flux, namely Atom, with a learning rate. This is the optimizer. And then for 500 iterations, you can actually take the gradient right here. So again, the loss function will be a half times A times F theta Z minus B square. So this is the half of the square of the residual. And this is a one norm. Well, you can play around a lot of things, but this is just to show that we can make things work, right? We can promote the sparsity on our result, which is FZ. And then we can add another penalization on the two norm of theta to make theta as a white noise. Well, you can choose different parameters here, but in the end, the takeaway message is Flux and basically knows how to take the gradient with respect to this complicated function value, because we've already taught Flux how to differentiate through A. And Flux knows how to differentiate through F because it's network. And Flux knows how to differentiate through this norm because these are all Flux functionalities. Like they're also defined in PyTorch or TensorFlow, right? And then Flux can differentiate through everything in here to get a gradient. Then you can update the parameters theta, which is the network weights, by this Flux optimize update. And then if you run this 500 iterations, you can get a solution by FZ. So you set up F in the test mode, and then you can actually calculate this FZ. This FZ will be your solution right here. So you can plot this solution. Well, it doesn't look that good because I definitely believe there are a lot of parameters or network choices that you have to carefully choose. But in the end, we show that this also works. Like you can actually incorporate these Jolly operators with very complicated networks. You can actually work on different layers. You can apply a network on the left-hand side of Jolly operator. Doesn't matter. Although things are complicated, Flux will know how to differentiate through the complicated network because we've already taught how to differentiate through these Jolly operators. So if you want to understand more about Jolly, you can look at the reference guide. And there are also some other applications of Jolly, for example, loop-unrolled seismic imaging, where the seismic imaging operator is defined as a Jolly operator, and it's intertwined within a very complicated network. And you can also read this publication that describes the basic concepts and ideas on how to do these software abstractions for Jolly and some application scenarios. Okay, that will be the tutorial for Jolly. We can actually take some questions if there's any, but I'm okay to proceed to the next one if there isn't any question. Okay. Let's then proceed to Judy. These names are actually very easy to pronounce, right? Okay. Judy is a framework that is built for large-scale seismic modeling and inversion, and it can actually scale to very large 3D industrial size. And our research group actually collaborated with a lot of people to make this happen for a large-scale 3D problems, for example. And then I want to say that Judy is actually based on DeVito, because when you do the seismic modeling and inversion, you solve a lot of wave equations, right? And Judy actually interfaces with DeVito, namely the wave equations are solved in DeVito. And Judy actually does this by following PyCalls. So in Julia, you can actually call Python lines or packages or functions very easily. And then Judy actually adds these linear algebra abstractions so that these modeling operators or migration operators, they're defined as linear operators. And you can use them in a very abstracted way. So for example, if I don't understand seismic migration or full inversion, I don't understand how that process is going on, I can still work with these abstracted operators and try out different algorithms to solve the problem. So let's go into some of the details. The Judy software is published here in a geophysics journal, and you can also check the Judy reference guide. So in this tutorial, I'll basically talk about how to set up these geometry acquisition in a small seismic experiment, and how does Judy do these software abstractions so that you can write code in a very clean way, and also talk about a little bit about the parallelization in Julia. We'll set up a mini cluster to run some of these experiments. So let's start by loading these packages and talk about the structure of Jolly. So we first want to set up a physical grid for simulations because we work on true physics, and these. So as the Tuesday tutorial already showed, DeVito uses finite difference operators to solve for wave equations, for example. So we like here we will set up a grid, which entails a shape of the grid. So you have these many grid points in your system, and you set up a spacing. So in this case, it's 10 meters by 10 meters in your model, and you have an origin. I typically set up to be 0 and 0 because we can always assume the starting point of your model is 0 meters in the lateral position and 0 meters depth. And after you run this, so this basically is some metadata you want to set for your model, right? You have a velocity model. You want to propagate the wave fields. You have to know the spacing of your discretization and the shape of your model, right? And then the next thing to set up is a physical object. So Judy actually defines a few types to handle these physical objects that you will see in these seismic modeling and inversion. One of them is to set up a model, and some other ones, including Judy vector, are also quite interesting. So the type physical parameter is an abstract vector which behaves like a standard vector, and it is used to store the velocity models or squared slowness models if you work with acoustic wave equation. So by abstract vector, it actually works the same way as a standard vector, but it entails some metadata. So we can first set up a velocity model like this. We can set up a velocity model that is water speed. So this is kilometer per second. We can set up a velocity model as water speed at the first layer, and then the second layer. So this is a 2D example. So first dimension is x, lateral position. Second dimension is depth, z. Second layer is 2 kilometer per second. Third layer is 2.5 kilometer per second. Then you can set up a physical parameter here, which is VP, the p wave velocity, and the spacing as we define above 10 meters, and origin. Okay. Then we can use the plotting tools in Julia to plot the velocity right here. So we can first plot VP, which is a matrix, right? It's pure Julia array. And the second thing we can plot is this capitalized VP, which is a physical parameter defined in Judy, which entails metadata. So if you plot them, you can actually use the same syntax, and they will give you the same thing, because this VP as a physical parameter behaves exactly the same as if it's a pure Julia vector, right? And what's fancy about this VP is, if you consider the capitalized VP as a physical parameter, right? It does not only contain the data itself, namely the velocity, also contains the size and origin and spacing, these metadata. So it's a vector equipped with metadata. But if you just consider the VP here, the small VP, which is pure Julia matrix defined here, your VP is actually just the matrix itself. It doesn't provide you any grid spacing information, or where does it start, or what is it for. This is just a Julia matrix. You have no idea what it stores, right? But this VP, capitalized VP, is a physical parameter that you can, you know, it comes with an origin, with a spacing. Oh, it's a model in the Earth subsurface. So basically, this is the Earth subsurface, water layer, and 2 sedimentary layers. That's the benefit of these abstract vectors. So if you want to know more about abstract vectors, I also suggest you to look at the Julia's documentation. And as we just discussed, you can do all sorts of things on these abstract vectors, VP, which is a physical parameter, but it's just abstracted, right? So you can do all of these computations. Norm, take the maximum, minimum, do a dot multiplication, do a square. You can also do all of these linear algebraic things onto this VP. Although it contains metadata, it knows how to do these things for sure. And then you can actually set up a model structure that wraps these different details, right? So the model is contains a shape, the spacing, and origin. And right here, I put squared slowness because that's the way how Judy solves wave equation. It's parameterized by square slowness. And NB is the padding grids on the sides so that you don't get boundary reflections. And this is the model. Now we have a model. We can generate shot records, seismic data, right? Okay. And in this script, I'll basically generate the shot records on the fly by setting up these source receiver positions. But in the next one, I'll talk about how to do this with SegWi.io files. Okay. For 2D simulation, everything, the wave propagates in the 2D plane, right? But we still will set up a y direction, which is always 0 because it's only a slice. Okay. Now, in this case, we set up 11 sources, and we set up sources equispace distributed on the surface at 12.5 meters. Okay. Then Judy actually uses these acoustic sources as cell arrays. So you have to convert the sources into cells because they're far, I assume they fire independently, But if they fire simultaneously, then you don't have to convert to cell. So convert to cell is basically to set these sources to fire independently. Okay, let's run this cell. And then let's set up the ocean bottom. So we have 101 receivers in this case. We can also evenly distribute them at the ocean bottom. Again, y direction is 0 because this is a 2D case, although 2D can handle 3D case. So if you work with 3D, then this tutorial doesn't have enough time for us to run the 3D simulations, maybe. Well, inversions, definitely not. Okay, and then you set up a spacing times 66, which is the ocean bottom grid, times once. So this basically means you put your ocean bottom nodes at the ocean bottom because this is the index of the ocean bottom. Okay, then the next thing is to set up a recording time and a time sampling rate of your shot record. So this is basically 2 seconds and 4 milliseconds. Okay, after we set up the source and receiver geometries, we can use these geometry objects in Judy to wrap these up. So this is to set up a source geometry, X source, Y source, Z source, sampling rate, record time, and this is to set up a receiver geometry. So in this case, we assume all the ocean bottom nodes are seen by all the sources. So we'll just put n source equals to number of sources equals to 11 right here, so that all the receivers, all sources see the same receivers. Okay, after we run this, I think I forgot to, this happens sometime when you work with Jupyter notebooks. You forgot to run some cells, but yeah, shouldn't be any error. Okay, now we can visualize the geometry onto the model like this. So this is the model as we just discussed, receivers, sources. Great. Now we can set up the source wavelet at the source locations right here. Okay, we can use a Richter wavelet, which is also defined in Judy. You can use different ones. And this is to set up a central frequency of your Richter wavelet, and you can plot the wavelet right here. Okay, it's a bump. Cool. And now we can set up these Judy vectors. So Judy vector is also a structure that stores the data, in this case, wavelet, but also comes with metadata. So if you set up this Judy vector with the source geometry and the wavelet, it will basically tell you this is a Judy vector with 11 sources. So again, you can access the wavelet by Judy vector.data. You have 11 sources with each wavelet. And this Judy vector also comes with geometry. And you can access the locations of the sources by this geometry. So again, this is not a pure Julia array, but it stores its data as a Julia array, but it comes with other geometry instances. And now we can actually do this linear operations for this wave field simulations. So if you are familiar with seismic, the way that the data is generated is by, first you have a source, you inject the source into the whole field by this PS adjoint, which is injection, and you solve a wave equation right here, AM inverse. A is the wave equation, parameterized by slowness squared. And then after you apply this inverse of wave equation, you get the wave field everywhere. You restrict the wave field by this projection operator on the recording time and recording location, namely receiver locations. And these are actually all linear operators, although this AM is not linear with respect to M, but linear with respect to the source. So we can actually build this as we speak. So we have this PR Judy projection, which is project to receiver geometries, PS, which is another projection, which is project to source geometries. Its adjoint will be extraction from this source Q. It basically projects the source Q into the entire subsurface. And A inverse is the Judy modeling takes the model. So model is this M, and also metadata. And this Judy modeling basically defines this A inverse here. Okay, these are all defined. Then we can check the math here. PR, A inverse, PS adjoint, Q. Okay, do the same thing. PR, A inverse, PS adjoint, Q. This will generate the data. So all of the idea right here is this PR, A inverse, PS are abstracted linear operators by Joule. So they are linear operators, they have metadata, they have adjoint and forward evaluations, and Julia doesn't even notice that they are linear operators. Julia just sees this sentence and say, well, I know how to run this. There's no problem with that. Then after you run this, you can actually get the data in the end. So this is the DOPS, which is also a Judy vector, comes with the shot record from different sources and also the metadata. So it comes with 11 sources and also the metadata. You can also combine these three operators in a single operator F. Okay, you get a forward modeling operator, which directly maps the input source to the output recorded data. And then you can actually, well, this takes a while, so I don't plan to run this. So you can actually only run one of the source experiments by taking the index of that. For example, the 6 is means the 6th source in your 11 sources. So this is basically taking the middle source, and also Q is taking the middle source. So in this way, you can only run the forward modeling on the 6th source, on only one of them. So right now, you only get one source. So this DOPS 6 will be the same as if you have DOPS and takes the 6th of it. Okay, then we can actually plot the data right here at different locations. You can see these two reflections, first one and second one. Okay, next thing I want to talk about is parallelization. So you might already notice that since these sources fire independently, you can actually fire them in parallel in the computer because they don't really interact with each other. So in this case, we're using this package in Julia called distributed, and you can actually set number of workers in Julia. So in this case, we first take out the number of threads in Julia, and we set up 2 workers, and n workers equals to 2. And then we say, okay, I want to display the environment variables right now, and I want to bind the threads into these workers. So basically, I have 12 threads on my laptop. Then first six of them will bind to the first one. The rest will bind to the second one. And this add procs basically means you add the processors, and you add 2 workers into your environment. And you can actually show these workers, which is number 2 and number 3, because the main process is number 1. And then right here, you basically tells Julia how to bind your threads into the workers. So this basically means I have 12 threads, namely 0 to 11 on my laptop. The first 6 of them is bind to the first core, the first worker. And the rest of them from 6 to 11 is binded to the second worker. Okay, great. And now you have 2 workers, number 2 and number 3. You will use everywhere so that they all load the distributed package and Judy package. Okay, now we expect that this can be run in parallel. Namely, I have 11 sources. Maybe the first worker can run 5 sources. Second worker can run 6 sources because they are in parallel, right? Okay. Now, if you set this up, you have 2 workers. then this will run in parallel. Namely, the workers will run independently for different workers. We set up a routine so that things run in parallel in Judy. Okay. Although you have to have enough memory, especially for migration, because if you don't have enough memory to run two things in parallel, then these two workers will compete for the memory. Then in the end, you still don't get parallelism. But if you have enough memory, you run migration, things will run in a parallel way. So the next thing we can show is the reverse time migration, which is which is RTM. So reverse time migration is a seismic migration method to map the dipping events in the data, as we saw about those 5 figures, to the Earth's subsurface reflectors. And the way we set this up is to set up a Judy Jacobian with the forward modeling operator. Remember, this F is PR, A inverse, PS, the combination of these 3 operators, right? And this Q is the Judy vector, which is the source. And then you set this up. This is the forward of it will be the linearized form modeling, and the adjoint will be the reverse time migration. So basically, you can again write these very clean algebraic abstractions. This is your data. You want to do a migration. Why don't you just apply the adjoint of the Jacobian times the ops? Perfect. That's a migration. And that's written in a very abstracted way that if you understand linear algebra, you don't have to understand seismic migration. You can already do this reverse time migration. And then this might take a while because it's 11 sources, okay? And then it generates a physical parameter again with some metadata. And then you can actually plot the reverse time migration image right here. These are the source imprints. This is the first reflector in your image. And there's also a second one, which is very dim, but it's right here. Okay, so this is a tutorial for Judy. Basically, the takeaway message is you can set up the source and receiver geometries, wavelets in Judy following this notebook. And also, you find that these seismic data generation is actually you can write this beautifully with these linear operators parameterized by discretized wave equation, right? And our concept is, since you can write this in linear algebra, you should also write this same thing in your code, namely here. So that's our ultimate goal of writing code as clean as possible and as informative as possible, because while we read the code, you know what's going on, because these are just linear algebra abstractions. Okay, this is the introduction for Judy. Next one, I'll talk about SegWi.io. So as we just discussed in the previous notebook, we discussed how to generate these seismic data from setup source and receivers, and then we can also do it in another way. We can actually load a seismic data from SegWi file through this SegWi.io package. So this is a package, again, under the Screen group, but it's basically, you can find different versions of these SegWi.ios. For example, there's also SegWi.io in Python. So this is a Julia package for read and writing the SegWi files, which are commonly used by seismologists. So they have pretty complicated file headers and things like that. Okay, and we're gonna show how to interface these SegWi files into Judy. Now let's begin by loading these packages, Judy, SegWi.io, and PyPlot, and then you can run this script. So this is again to run shell in Julia. You can run this thing to download the data and unzip the data into your system. Okay, I think I've already installed them. So downloaded them, so I don't have to do it anymore. And then there's a function called SegWi-read, which reads the SegWi file over here, reads it into a shut. Let's do this. So you can see this shot is read by the sec_y read function as a size block. So again, this size block is a structure that contains some data and also metadata, namely the file headers. You have, for example, sampling rate, you have number of sources, you have a lot of these metadata right here, and you have different file trace headers. Yeah, and you can actually access these file headers by running shot.file header. Then you can extract these file headers out of that, right? And then you can actually run shot trace headers 10 to get the 10th one in your sec_y file. So the 10th shot in your sec_y file. Makes sense, right? And denotes the source position and receiver positions and sampling rates, for example. Okay, then we can also extract the extra headers from the sec_y container. Namely, you can get the header by shot get source X. So this basically gets the source X from all these complicated paragraphs. Similarly, you can get receiver and time sampling rate, and you can set up number of time samples times your time sampling rate. This will be the recording time. So you can extract these file headers easily by this get header function. And then in the end, you can plot the seismic data stored in the sec_y file by calling .data on this sec_y blocks that is loaded in the sec_y IO. So you can actually do a plotting here. This shot.data basically takes the seismic data and this float32 basically translates that into pure Julia arrays. And you can see this is a source at this number of meters. The time goes like this. So the source is firing something like here, and you can see these structures. This is a BP data, so it's very large. It's recording, it's 8 seconds. I personally never worked with that long of recording data. Okay. And we can also have these sec_y scan. So the scanner is designed to be multi-scale, meaning that your workflow will stay the same regardless of the size of your data, basically. So you can actually do a directory scan. So this is the directory that contains a lot of seismic data. And you can have a file filtering. So there will be a lot of this sec_y file called BPTTI something, and you can actually filter them. And you can choose which keys you want to get access after the scan. So you can choose these many keys. And then you can actually scan the entire directory right here with the file filter of BPTTI and only scan these keys. So by running this line, you can see you can scan a lot of files in this folder, BPTTI, with 1200, 1201, a lot of sec_y files in this system, and you scan for these keys and with these filter of with the filter of BPTTI. Then you can actually see you found all the files in the directory, and you can actually check how many shot records did you scan in this period of time. You scanned 111 shot records. And then you can actually extract the global information such as source positions from all of these sec_y files by this. Okay, this is X position, lateral position, and depth. Well, we always fire this source on the top of the model, so it's 0. And then we can actually wrap the sec_y container into Judy vector and use it for inversion. So this is quite simple. We just load this sec_y LU by scanning, right? And notice that we haven't read the data into the Julia environment yet. And because we don't want to do that, because this might take you a lot of memory since the seismic data is very large and you have multiple of these sources, this will blow up your memory really fast. So Judy vector can still take this segy LU, which represents the segy files, but you haven't loaded the data into the memory yet. Okay, so now the D to TI will be a Judy vector, and you can take a number of sources in Judy vector, geometry, and data in Judy vector, basically. And now, if you create, now this is a Judy vector with metadata, but its data is not loaded yet. So I'll explain that in a little bit, but basically you can set up the source geometry by applying the geometry in Judy onto the data you have. Take the key of source, and you can set up a Ricker wavelet based on that. So this Q will be a Judy vector set up based on the source geometry of your segy files. And then the interesting part is we haven't loaded all the data into the Julia environment yet because these segy files are just pretty large. But the way you can work with it is you can load one of them. For example, the shut ID equals to 47 out of this 111, and then you can do a get data so that this Judy vector loads the 47 shut records into your Julia environment. So if you load it one by one, it doesn't blow your memory that much. But if you load entirely 111 sources into your system, then it's your Julia system will basically find a very hard time to take these all into your memory, right? And after you get the data, you can actually get the source location by calling, because this shot again is a Judy vector, it's equipped with geometry, this metadata, you can get the source locations and receiver locations. Quite clear, right? And then you can actually plot it in like this. So you plot the shot data, since the data is already loaded into the memory now, so you can plot it with correct labels and such. So again, we plot the same piece of data, but the first time we actually directly load the data into the memory. The second time we scan a lot of these segy files, and then we only load one of them into our memory. So we get still the same shard record because it's at the same location. Okay, that's so much for segy.io. If there's no question about that, I'll go into my last tutorial about normalizing flows. So the idea of normalizing flow was actually raised quite recently, like in this decade. And our research group basically noticed that the normalizing flow is quite interesting because it's a very powerful generated network that can be used for geophysical applications. For example, when you solve an inverse problem, these normalizing flows as a deep learning tool can provide you with a learned prior according to your pre-assumptions on the model or or training data sets. So this normalizing flow is actually a very powerful tool, and our group has a couple of publications on how to use this normalizing flows for seismic imaging, ultrasound imaging, and photoacoustic imaging. A lot of these imaging and inversion problems that is involved in inverse problem community. So in this script, I'll basically show how to abstract these normalizing flows in the package called invertible networks right here. So I think it's very well documented, and it shows a lot of publications that uses invertible network idea, like seismic imaging and uncertainty quantification, a lot of things like that. And feel free to browse in to check the latest work. So let's start by loading these packages. Again, we should do it all the time. And there's also another YouTube presentation in JuliaCon 2021 if you are interested to see what's going on. This is not only, this can also be applied to other communities like medical imaging and stuff like that. Okay, so first, don't worry too much. It's a normalizing flow. So let's discuss what is normalizing flow first. So normalizing flow is a type of invertible network that contains a series of invertible layers. So by invertible network, I mean, suppose you have an x, you apply this network g theta, you get a z. Then since this network is invertible, if you apply g theta inverse on your output z, you get the same x back up to numerical precision. So that's why we call it invertible network. And the forward and inverse evaluation of these g theta, neither of them should be very expensive. So they should be both cheap. And then why is this normalizing flow very important? It's because after you can actually apply these normalizing flows to learn a distribution of something. For example, if you have a lot of these cat images, like different cats capturing it at different motions, and you want to learn the distribution of all the cat images so that you can detect which cat, if I provide you with a cat image, you can detect whether there's a cat in the image, or you can say how likely there is a cat in the image. Then you may want to learn the distribution of the cat images. So the idea of the normalizing flow is after you train the normalizing flow to map your cat image X by the normalizing flow g theta to a latent space Z, which is the normal distribution. So your concept is to map the cat distribution to Gaussian distribution. Then in the end, after you train this network, suppose you train this very ideally, you can sample new cat images from the Gaussian distribution, because you can just easily sample an instance from the Gaussian distribution, namely a white noise, and you can apply the inverse of your normalizing flow, then it will give you something in the cat distribution, namely cat, which you've never seen before. So this is the idea of the normalizing flow. Our group also extends this idea for seismic imaging, namely you have different you have different Earth substructures. You might want to learn a prior distribution of the Earth substructures. Then you can actually provide a lot of these Earth reflectors, layers, and then train this normalizing flow. And after that, you can draw samples of the Earth substructures by passing a white noise through the inverse of your g theta, your normalizing flow. So this is the idea for why we want to train a normalizing flow. And in this notebook, we're going to do a very fast training on a very small scale example. We're going to work with this 2D Rosenbrock distribution, because training all these cat images or seismic images will take you easily thousands of dollars. Now we can do this training right here. So we set up n training points as 60,000, and we call this a banana distribution, which is actually called Rosenbrock 2D Rosenbrock distribution if it's in formal terms. So we call it banana distribution because it looks like a banana. So most of the points are clustered over here, and it follows like this shape. So this is basically a probability distribution in 2D, and we can plot it. Yeah, for sure. And now the normalizing flow actually is trained to map the points in this distribution to a white noise in the latent space. That's the concept of normalizing flow, because it's trying to normalize the input. That's why it's called normalizing flow. So the training is based on some change of variables formula and expectation, and you approximate this expectation by something like MC Monte Carlo samples. There are a lot of math, but I know this is not a math conference. So basically, a short answer to what we're training for is we want to pass a random samples from your target distribution, namely this banana distribution. You pass the samples to the normalizing flow. You get an output, and you want that output to be white noise, namely the norm of it should be 1. So in the end, that comes with the optimization function. So this 2 norm on the output of the normalizing flow corresponds to the Gaussian distribution, and there's a log determinant term according to the change of variables. There are some math, but I won't go into there too much detail. So this is the way you write a loss function in the Julia. So you do G, which is the invertible network. You do forward on X. It will provide you an output in latent space called Z and the log determinant term. And your L2 loss, which is assuming your output is Gaussian distribution, is this 2 norm square on Z. And you can basically back propagate your loss through this DZ and Z. So basically this sentence will set up the gradient for G with respect to its network parameters. So in this way, this loss returns a L2 loss on your Gaussian assumption on Z and log depth term. So next, we can set up, did I run this cell? Yeah, okay. Next, we can set up these network structures. We have input channels, because this is 2D, this will be 2. Hidden layers, well, some machine learning details, flow steps, some details. And this is the glow structure, taking all of these. So basically this G will be the normalizing flow that you want to train. And its parameter is theta, which is hiding below. Okay, and then you set up some training parameters, Maxwell filtrations, learning rate, optimizer you want to use, Atom, and then you can train it right now. So basically in each iteration, you pick some random batch from your training set here. You compute the loss function right here, and then you set up the take the terminal log, and then you print it out. Then right here, since this loss already computes sets up the gradient of the network parameters, you can just do update for P in all the parameters in G. You update all of them. So let's run this now. This might take a little while. So this is to basically print out every 50 iteration in your training. And you can actually check your training objective log to see whether you get convergence or not. So you have various ways you can train your network to see the objective convergence of the objective. And you can also check the normality of your output, because your normalizing flow aims to output normal, an instance from normal distribution. So you can just check whether you pass a training sample in your distribution through the normalizing flow, does it provide a normal distribution? Okay, so this training seems to be quite fast because we only need 400 iterations. Okay, I think it's already done. It's trained. Since it's a 2D example, it should be fast. Okay, we can plot these metrics to see whether we get the convergence. Again, these are from from PyPlot, which uses the matplotlib library in Python. So you can check the L2 norm of your output of your normalizing flow, and you can find the L2 norm of your output is roughly at 1, which is what you want, because you want the normalizing flow to output Gaussian noise, and Gaussian noise has a L2 norm of 1, right? And you also have a log that term and the full objective. Okay, the full objective is going down, which is cool. And then you can actually test out the normalizing flow right here. So you can draw 500 test samples. You can generate them by random. This basically randn will generate random samples from Gaussian distribution, and then you can pass them. You can plot them first to check that they are actually Gaussian distribution samples. So this is Z1. This is first dimension, second dimension. Well, this bump looks like a Gaussian bump, right, from Gaussian distribution. And in the test time, we'll pass these samples in the Gaussian distribution by the inverse of the normalizing flow. Remember, we have an invertible network. So by passing these Gaussian distribution samples through the inverse of the network, we're supposed to get the samples in the target distribution. So let's try that. So again, G dot inverse on these test examples we plot above. This will generate some samples called X test, which should be in the banana distribution. And then we also have a pretty figure that shows how these samples are matched to the ones. So basically, this is Z. This is the output of your. This is from white. This is white noise. This is from Gaussian distribution, and you pass them through the inverse of the network. Then it will generate something in the domain where you should see a target distribution. So this shows how they are mapped to each other. Great. And then you can actually check whether the generative samples of X actually works. So the blue dots is actually the correct samples from the distribution, and the yellow samples are actually generated by random sampling white noise from the latent distribution and pass through our trained normalizing flow. So this, you can see that these yellow dots, which are generated samples, are pretty good. They fit the distribution very well. So in this case, we train a very good normalizing flow. And you can generally apply this idea to image mapping. So basically you map a cat image to an image of white noise. If you train that very well, then passing white noise in your latent space to the inverse of the network will give you the cat images, the generative samples of cat images also very well. So these ideas have been applied to photoacoustic imaging, seismic imaging, wave equation-based inversion, things like that. And one of the fancy things about invertible networks is, since the network is invertible, you don't have to, when you do the backpropagation, it's quite simple. Because suppose you have a very large network, in your forward evaluation, you pass your input to every layer in your network. You have to store the intermediate variables of each state, each layer. Then when you do the backpropagation, you will compute the gradient according to the value of that layer, so that you can backpropagate the gradient. Then the memory might blow up if you have a very large network and you have a lot of these layers. So for invertible network, since every layer is all invertible, you don't have to store any of the intermediate state in your invertible network. When you do this backpropagation, you can recompute the state at each step because things are invertible. Every layer is invertible. In this case, you can backpropagate and recalculate every state, and you can still backpropagate the gradient into the input. And then in the end, while training the network, you only have to know the input and output of the network. You don't have to store anything in between in the intermediate layers. So this is one of the benefits of training a normalizing flow. So if you use the networks in the invertible networks package, you'll find that benefit in your results ultimately. Okay, so this concludes all of my tutorials. I think I pretty much land on time. And I appreciate any questions on Slack, or you can reach out to us on our GitHub repository. So if you find anything interesting in our software stack, you can actually check our GitHub repository. And if you find any issue, you can open issues or pull requests under the GitHub repository. And welcome to talk to us. And thanks again for Software Underground and Agile for giving me this opportunity to share a lot of the research work in my group. I hope I still catch everyone.
All right. So thank you very much. If you can stop your share. Cool. Thank you very much That was definitely a bit of a whirlwind tour. Lots of interesting, cool stuff in there. So, if you haven't seen Julia before, hopefully this has whetted your appetite. Do reach out to the Slim group. You can also have a look on the Software Underground Slack. The links are down below. If you found this useful, please do feel free to share it. If you're watching this live, then these videos will stay on after, so they're not going to go away. So feel free to share with people who might be interested. We have one more talk later today, and then there's still some other things related to Transform 2022 happening, but this was the second last of our tutorials. So do go and have a look at the ones that have happened throughout the week. There's been some really good stuff. But otherwise, thank you again to Francis for a very interesting talk, and we will see you around for something else. Have a good day, everyone.
Cheers.